All right. Now I lost my, okay. Let me just, okay. So I'm going to talk today about the NASA ISRO SAR and specifically for polar studies. I'm the NISAR cryo lead. Unlike some science teams where there's a single lead, there's so many disciplines. We have multiple leads. There's maybe about 20 people on the science team, and we have 4 applications areas, which I'll talk about in a second, but I'm the cryo lead. So NISAR is a partnership between NASA and ISRO, the Indian Space Agency. We have 3 main sets of science objectives focused on ecosystem structure, things like biomass and forest disturbance, cryosphere, which includes sea ice and ice sheets, which mostly what I'll talk about today is ice sheets, and then the solid earth, which is earthquakes, volcanoes, things like that, and that you can measure the deformation with SAR interferometry, which I'll talk about a bit more too. Then there's a 4th area that's was added in the recent science team, which is applications, which covers all sorts of things. And the lead for that, Kathleen Jones, has been having all sorts of workshops with the USDA, the U.S. Forest Service, NOAA, the National Ice Center, all of the different government agencies that would be using the data more in an applications kind of way rather than in the science, one of these specific science disciplines. So the mission will launch around December 2021. It's a dual band L and S band radar with a L band radar from NASA and the S band created by the Indian Space Agency. There's some other technical details I won't go into, but it's a 3-year mission and it's an freely open data policy. Again, it's L-band and S-band, 24 centimeters and 12 centimeters. The L-band 24 centimeters is designed to optimize things for SAR interferometry, which can be degraded as the points in the area you're imaging as they move around on the scale of wavelength. So if you think of leaves blowing on a tree, if the wavelength is C-band at 5 centimeters, you're going to have much more disturbance than relative to the 24 centimeter wavelength, which might be able to tolerate some movement of the leaves. It's a fully polarimetric SAR. The primary mode will be a dual pole mode, so like and cross pole data, but it can do single, which is mostly what we use on the ice sheets, and it can also do some quad pole data. Has a 12-day exact repeat, which is good for SAR, and it's the most rapid repeat you can get and still cover the full Earth with the 300 or 240 kilometer swath, which makes use of what's called a sweep SAR technique, which is, I won't go into detail about that. It's sort of like ScanSAR, except it lets you maintain the full resolution of the radar. ScanSAR, typically you degrade the resolution. And here's a picture of the instrument. It's a large reflector in space. It's a 12-meter diameter sort of like umbrella thing that folds out, and the white things sort of on the top side of that tube there are the radar feeds, which reflect off the antenna then onto the ground. It's a fairly systematic observation plan. This is sort of a notional, it's not the exact plan, but it's notional. We have a sea ice mode and some ice sheet modes, but most land surfaces will be covered at 25 megahertz resolution for every single, basically the radar is supposed to be on all the time over land. Because of some limitations on the data system, I think they've reduced that a little bit to it's on all the time, and I think descending mode and every other ascending mode pass every 12 days or every 24 days in ascending mode. But it's an incredible amount of coverage, unlike many missions today where they either cover things frequently or they have large gaps in spatial coverage. And then you'll notice some different colors in India, and that's because India has a lot of very specific applications for the radar and different modes, so there's a lot of mode changes there. This is sort of a compromise plan, and it gives good coverage for everybody all the time, but it won't always, there will be people who may be disappointed somewhat with a particular mode, but it's designed to optimize over all disciplines and produce a consistent time series. And it's going to collect something like 50 petabytes of data over the course of the mission. So what is a synthetic aperture radar? If you fly a radar in space, typically it would have a physical aperture or antenna size of about 10 meters. In the case of NISAR, we saw that it was 12 meters. but it would illuminate an area on the ground that's several kilometers wide, as shown in this yellow on this track on the ground. But if you save all of the pulses along track, you can actually synthesize an aperture 4 or 5 kilometers or more long and get very fine resolution in the along track direction. And then in the across track direction, the resolution is determined by the bandwidth, which is directly proportional to the pulse width, or inversely proportional, I guess. So bigger bandwidth gives you a narrower pulse, and most stars typically get about 3 to 25 meter resolution. And this just gives you an example of what a SAR image looks like in Antarctica. This is Hemin ice rise. It's at the edge of the Filchner-Ronne ice shelf, and there's the area to the left is a stationary point, an ice rise, and the ice is getting ripped apart. Actually, there's a little ice rise in the middle there. The ice is getting ripped apart as it flows past that ice rise. So SAR interferometry makes use of the fact that if you fly the SAR by and then on a second time fly it by, say 12 days later in the case of NISAR, in a nearly exact repeat orbit, and it's something we're really striving to get with NISAR. We're using a lot of effort to control the orbits within a tube of about 250 meters diameter. So as long as the SAR flies by in close proximity on the second pass, and the surface doesn't change that much. So for example, it wouldn't work on the ocean where the ocean waves are continually rearranging themselves unless you flew by within a few milliseconds. But on most surfaces, things stay coherent, and you can actually difference the phase of one radar return from the phase of the second radar return. And that phase difference is sensitive to both topography and motion. So what you see here is back to Hemin ice rise again, and you can see the sort of broad fringes on the left, center left. That's where the ice is not moving very rapidly, and then these fringes, which are sort of like contours of the speed of the glacier or the ice shelf with the interferometric phase. In this case, it's pretty flat, so there's not much effective topography. That's another reason to keep the baseline short, because it's sort of like a stereo effect. So the closer you fly the satellites together, the less topographic effect you have. But basically, in the end, what we have to do is use a digital elevation model and model the topography and subtract it out, and then we get the motion signal. We also use what's called speckle tracking, which is a kind of a close cousin of SAR interferometry. And it's like the feature tracking that maybe Ted will talk about today, where you cross-correlate patches of images to look from changes or something moving from one point to the next. But an advantage of SAR is that the SAR has a speckle pattern or a grainy texture to it, which is often considered noise. But if you maintain the same requirements for interferometry and the images are coherent from one image to the next, you basically get the same speckle pattern. And you can track that speckle pattern, and it's very well correlated, so you can get pretty good accuracy in the offsets. Disadvantage of this technique is that you need bigger patches to cross-correlate, so you don't get as good resolution. But the advantage is you get both motion in two different directions. With the interferometry, you're only looking at motion that's directed along the radar line of sight, so you would need multiple viewing geometries to get a vector estimate. So for the past 10 years, and we just got funded for 5 more years, I've been working on the Greenland Ice Mapping Project, which makes use of as much data as we can get from the global constellation of SARs. And much of these data are we can thank for the Polar Space Task Group for, which is something Ken Jezik started around IPY. And basically, a few scientists from each country and people from each space agency get together once a year. They formulate a set of requirements that each space agency can contribute their capabilities to. So there's specific ice sheet mapping requirements. Tends to work well in polar regions because there's not a lot of conflict with commercial systems. So we produce these velocity maps regularly. We started with sort of fairly sparse data in 2001. And we've been increasing the density of the coverage as new sensors have become online. You can see the latter ones at the bottom of the screen from where we now are using Sentinel data get almost complete coverage of Greenland when we combine it with also Landsat data as well. And in the top right, you're seeing a 20-year average. It's the most accurate map we have by averaging all the data from 20 years. So the reason we need time series, Jakobshavn and ISRO is a good example of why we need time series of glacier speeds. At one point, when I started out, textbooks sort of talked about glaciers changing on scales of centuries, millennia, and we see that they change actually far more rapidly. We started out with some ERS data when we were lucky to have one measurement in a particular year, or there were many years we had no measurements. And the glacier was moving at about 4,000 meters a year. So what you're seeing here are points, the speed of the glacier through time, and the colors in the plots correspond to the locations on the map in the upper left corner. So then we had some data from Landsat 7 that Mark Fahnestock processed, and we saw that the glacier had increased its speed significantly. We saw even more increase in speed as RadarSat 1 came online. And with TerraSAR-X now we have regular sampling, and you can see that not only is there an overall change in speed, but there's a lot of strong seasonal variation as the glacier advances and retreats each summer. And trying to understand the processes that give rise to these kind of variations is really important for trying to understand why this glacier has sped up so much over time. So as you can see, the average speed is, you can eyeball average that, it's probably about 10,000 meters a year now, up from 4,000 meters a year, which means the glacier is putting about 2.5 times more ice into the ocean as it was in the 90s. And in the 90s, it was more or less in balance. So this glacier, over a decade, was able to raise sea level by about 1 millimeter just from this one glacier, so, or 1/10 of a millimeter a year. So it's a large contribution. This is kind of the gold standard for the kind of observations we'd like, because we were able to focus TerraSAR-X with a little 30 by 50 kilometer scene on this one glacier, but we don't have that coverage for all of Greenland, or we haven't over time. We have looked at some other glaciers with TerraSAR-X, but within a much less frequent sampling. We might have 5 or 10 observations a year rather than 30 or 40. Fortunately, now we have Sentinel, and we're getting data every 6 days around the, oops, just lost my screen. Now we're getting data every 6 days around the entire coastline of Greenland, and then there's a hole in the center of the ice sheet where they're only acquiring data during the winter. But that's the area that's not changing with time, so it doesn't really matter too much that we have a gap there, because we can fill it in each winter. And we're able to produce annual average maps for the complete ice sheet, and then quarterly averages that are pretty complete, and then monthly averages, and then we can also produce 12 or 6-day averages from the data. And this is just an incredible change in the picture of things that we had just as little as 5 years ago, when we had really no coverage for some years. So the other area that's important for ice sheets, or for the polar regions, is sea ice. And this is a slide I grabbed from Ron Kwok. And I won't go too much into the details of what it's showing, other than I think it's showing deformation over the entire Arctic from the RGPS system, where he basically does cross-correlation of images, not on the speckle, but on the actual ridges and leads and things like that, over the entire Arctic basin each year. And it's able to get a time series of the deformation of sea ice through time. And that leads me to since we're talking about the Arctic, some developments that have happened with NISAR. So NISAR was baselined to be a left-right looking mission. Most SARs look right, primarily because sea ice in the Arctic has been a major goal for them to acquire. But NISAR was designed so it could look left and right. So it was going to look 25 cycles a year toward the Arctic and 5 cycles a year towards the Antarctic. And you can see in the Antarctic picture, when the SAR is looking right, we have a big hole, that black circle. And when it's looking left or south, we have the red circle, which is a much smaller gap, which we can probably close by also doing some acquisitions where we rotate the SAR a little bit further outside its normal operating range. Many SARs actually have, if you see maps of Antarctica, you'll see a huge hole in it, that black hole. So, and that we were going to fix by having these left-looking coverages. But the solid Earth community really did not like the shifting from left to right looking due to the fact that they want continuous time series, and it kind of disrupts the continuity of their time series to do that. They were afraid that we might have an earthquake, for example, during a period where they wouldn't have data. So they've advocated for going to a completely left-looking mission so we wouldn't have another hole in Antarctica. And the argument there is that Sentinel A and B, 1A and B, and the RadarSat constellation will cover the Arctic quite well, and that we could meet our requirements not using NISAR data, but so looking more holistically at the requirements across all of the sensors rather than requirements for a single mission. So we will now have a big, well, I think the mission is going to go to this. It hasn't been fully approved yet, but it's looking more and more like everybody's agreeing this should happen. So we will not get any SAR data from NISAR north of 77.5, and you can see that red dashed hole in the Arctic. So we'll miss the northern part of Greenland, which is actually for measuring ice velocity, it's the best place you could miss because it works the best with Sentinel. And the glaciers are generally fairly big, so the lack of resolution in Sentinel is not such an issue. And then, yeah, the sea ice will have to be filled in with the other sensors. Fortunately, we've looked into it a lot, and Sentinel is acquiring quite a bit of data now that almost meets the requirements, and the RadarSat constellation will come online in, I think they're launching later this year. So NISAR will provide a wealth of new data for both Antarctic and Arctic studies as well as global studies. It's a fairly repetitive systematic mapping. There won't be much room for special requests, but since everybody's area will be covered with 1 to 2 observations every 12-day repeat cycle, people should have more data than they've ever had before. And it's probably going to be left-looking, which means, as I just said, we'll need other SARs to meet our sea ice requirements. And I should also note that there are several other applications where for the Arctic, such as boreal forest biomass, that's one of our objectives, and disturbance meaning disturbance like cutting down trees or forest fires. Flood inundation and extent, and permafrost deformation. We can see as the freeze-thaw cycle, we can see the permafrost go up and down, and from that you can infer some properties about permafrost. And then, of course, the Arctic is not free of hazards such as earthquakes and volcanoes, so we'll certainly be looking out for those with the mission. And with that, I can take any questions.
Okay, great. Well, thank you so much, Ian. That was excellent. I'd like to save any major questions for after Ted's presentation, but are there any quick points of clarification that anyone has for Ian right now? All right, so we'll have a broader discussion after Ted's talk, if that's okay with you, Ian.
Yeah, we're going to get a TED talk.
What's that?
We're getting a TED talk?
Yay,
We're getting a TED talk. All right, go ahead, Ted.
Yeah. This up. I had some trouble. Sorry, I joined a bit late. I had to find a quiet room at the IGS meeting here in Buffalo, and then also had some trouble getting Wi-Fi to work inside the quiet room, which turns out to be a closet, basically storing a bunch of the tablecloths and stuff, but it's lovely in here. So I'm going to talk about visible near-infrared imagery and the upcoming Landsat 9 satellite, and what we're doing currently with the Landsat 8 satellite, and what we're about to start integrating with Sentinel-2 in terms of mapping.
Ted, I'm sorry. Yeah, do you want me to put your slides up, or are you going to share your screen?
Oh, didn't I? I thought I shared the screen. I guess maybe I didn't. Hang on. Oh, it's because it hides. Okay. And here we go. Do you see the screen?
Not yet.
Oh.
Yep, looks like it may be coming on. Yep, there you go.
Okay.
Thank you.
Great. So first slide, same talk. Landsat 9 is coming up. Probably will be launched in late 2020. It's being built now the sensor is being built now at Ball Aerospace, the main sensor. And Landsat 8 has already been in orbit for 5 years, and we've done quite a bit in terms of mapping ice velocity with Landsat 8. We're going to integrate Sentinel-2, and in fact, that's already happening, but it's not available in the way that the Landsat 8 ice velocity data is available for us. Let's see here. So Ian alluded to what correlation mapping is for radar imagery. Instead of a speckle pattern, what we have is an actual image of the surface. And what's great about Landsat 8, I've shown this kind of slide about correlation many times before, but what's different about Landsat 8 from Landsat 7 or Aster or Spot is that the radiometric resolution is quite a bit higher. And so we're actually able to see a version of the texture of the surface generated by sastrugi or by far more subtle crevasses than we were with the previous Landsat series and the other satellites I mentioned. That gives us a texture that, if it's permanent, if it stays there through a couple of cycles of Landsat, a 16-day repeat pattern, we can get a mapping through this correlation, a mapping of the displacement of the surface. And because we're tracking sastrugi, not just crevasses, we get a broad mapping of the surface of the ice sheet. The places where this has trouble are in places where the snowfall is very high. But having a smooth surface is no longer a problem. And I'm showing that here in this slide. So there's an area that I've zoomed in on. Those are not sastrugi from the Svalbard coast. They're a bit bigger. Those are from East Antarctica. But those two pictures side by side, sort of in the bottom, center, and right, are a comparison of Landsat 8 and Landsat 7. And in Landsat 7, when you looked at a place like the side of Svalbard Dome, that actually is, I believe that's, well, that's not Raymond. That's, oh God. NI stream D or bin shadow or ice stream. What you see in Landsat 7 is actually noise. Those pixel variations that you see there are not tied to any surface structure, and so they don't correlate between images. But in fact, in Landsat 8, because of the higher radiometric resolution, we're actually detecting a speckle pattern, if you will, that's based on the sastrugi. Landsat 8 has 15-meter pixels, so it's not resolving the individual sastrugi the way Worldview 3 or 4 does, but it's resolving a texture that's related to the sastrugi, and therefore we can track that and get maps that are much more extensive than the past Landsat maps. The other thing that's been improved in Landsat 8 is that the acquisition rate is able to be much higher than it was in the past. So the sensor's onboard recording system is has more capacity, and we're able to acquire a lot more data, and they do acquire and process the data much faster. The whole ground system for Landsat 8 support and for Landsat 9 has been improved, and you can see a comparison there of Landsat 8 versus the last year of Landsat 7 acquisition before Landsat 8 was launched, because the Landsat 7 pattern was changed after Landsat 8. And you can see that there's a big difference. This and the fact that Landsat data is freely accessible supports a huge number of applications globally. But in fact, for ice mapping globally, it's essential to have this long time series, this continuous record, and lots and lots and lots of images, because that way we can get around the problem of cloud cover over the images and get a fairly continuous mapping, and mappings over a fairly short time frame, like a season, or in some places even monthly mappings of ice velocity. So we're really pleased with how much more data Landsat 8 is able to acquire. And of course, adding Sentinel and Landsat 9 will make it even more possible to monitor the world's glacier flow speed easily. Okay. Able to do more easily with Landsat 8. This Landsats is request and receive ascending node data, so data that's on the upswing, if you will, from the South Pole area to the North Pole. That gives us more frequent coverage. Mostly, it doesn't really do a whole lot for velocity mapping, but we get more frequent coverage of key areas. The other thing we're able to do is point the satellite off one side and take a look at some areas that have never been imaged before by the Landsat program. And for Antarctica, that means being able to look about one Landsat image width closer to the South Pole, which takes the southern limit from about 82.5 to about 84, a little bit more than 84 degrees south. And it also, by off-nadir pointing, gets the top edge of the Greenland ice sheet. And we've been repeating that coverage midsummer for both ice sheets every year for the past few years. So there's some data that hasn't been looked at too much that's interesting. It's not that these areas have not been imaged before somehow, but not by Landsat. Ian also talked about this. First of all, making mosaics, and we have a nice mosaic of Antarctica. I believe that one is the one that Alex Gardner did under the same program that funds our Go Live project, which I'll talk about in a minute. And also on the right-hand side image, you can see how more frequent data, more frequent mappings, in this case of Greenland outlet glaciers, reveals a lot of seasonal structure in the ice flow and gives us a lot more to work with in terms of understanding seasonal changes and long-term changes in mass balance of the ice sheets and therefore sea level rise. So we're able to do a lot of cool stuff because we've got a lot of data, but it's because we have free access to the data. And that's been called into question recently. I think that logic will prevail and we'll continue to have free access, but it is being rediscussed in some circles right now. So the Go Live project, basically, we've taken the Landsat 8 data stream. We'll add in Sentinel-2. Sentinel-2 A and B are visible near-infrared sensors with, I believe, 10-year pixels, wider swath, and somewhat less global coverage, although I believe they're approaching full coverage of Antarctica now also. And we're taking all of the areas. In this case, it's a map of the Landsat path boxes on the global map. And the Landsat path road that covers an area of ice bigger than 5 kilometers squared, permanent land ice bigger than 5 kilometers squared. Can you all hear me okay? I'm seeing that is it okay?
Actually, Ted, I was going to suggest maybe, obviously keep sharing your screen, but maybe turn off your personal video, and that might help the bandwidth.
Is it really choppy? Okay.
It not always, but sometimes.
Okay. It's not bringing up that.
I think the lower left to turn off.
Yeah, I know, but it because I've got the PowerPoint on full screen.
I think I can do it. Hold on. Stop video. No, it didn't stop. Yep, you're off video now.
Yeah, good, okay.
But you probably want to go back to full screen. Yep, perfect, thanks.
Yep. So, Go Live project. We've taken all of the path rows that cover ice, permanent land ice, and we're running a time series of velocity mappings. When we get a new image, we look back in time. I believe it's 96 days for the Greenland ice sheet and for most of the world's glaciers. And then for Antarctica, we actually look back 400 days. That doesn't work everywhere, but there are places in Antarctica where that sastrugi pattern that I mentioned is actually stable and correlatable over more than a year. These are places that get very infrequent storms. They have big sharp sastrugi that are eroded by the wind that don't change very often. So we get a nice record because every single new image gets 4, 5, 8, 10 pairings where we at least attempt to get a velocity map. We gather those vectors and make them available online. Go Live has a couple of products. I mean, we have the individual mappings. That's an unusually good one of Bird Glacier there in the upper right. And then in the lower right, I'm showing one of our Antarctic mosaics, which we're about to put online. That's available by request right now, but we're going to have that online as a product fairly soon. And right now it's at 750 meter gridding, and it'll be 125 meter gridding. Probably before the end of the year. We're working on getting that running on our supercomputer at University of Colorado. So there's a couple of products that go along with the ice velocity that help with data quality. And that's what you're seeing in the center and the right side image there. Correlation peak height, in other words, how well did the two pictures match up over these little chips that we're comparing for structure. And then the difference between the best peak and the second best peak, that's indicative of how unique the match was. Usually that means you get a low noise vector map of the flow direction when you have a high difference between the two peaks. Another view of the velocity map. This actually, it says go live. That's one generated by AutoRift, but those two efforts, Alex Gardner's AutoRift, NSIDC's Go Live project, they're merged in the It's Live Measures Award that's coming up. And that's the change in velocity, again, using Alex's version of the Landsat 8-based mosaic. Recently, a paper came out, this was just a couple of weeks ago, it got published in Journal of Glaciology, taking the LISA mapping and doing a strain rate calculation over the ice sheet with some attention to the details of how the strain rates are generated, and also, well, in particular, what length scale you use, what size you use in order to determine the strain rate, and the kind of how you compare local vectors to extract the strain rate from the variations in flow speed across a small region. It's a beautiful map that Karen has generated. That will also be a product that's associated with our LISA data set that'll be online fairly soon, but it's available now if you ask. And that just shows you what I think is one of the prettiest little patches of messed up ice in the world as far as strain rates go. In terms of shear longitude. There's a lot of flow complexity there, but what you also can see is that there isn't a lot of noise in the final velocity field. And that's because, again, not to hit it way too hard, we get thousands and thousands of mappings of the glacier of the ice sheet over a fairly short period of time. And by averaging all of those and smoothing in between them, we get very low noise, very smooth velocity vector maps, which gives us a nice view of the strain rates. The other thing that we can do with a lot of data is take a look at the characteristics of glacier seasonal speed up and slowdown. I'm blatantly stealing from excellent work by Twyla Moon, and she has 2 or 3 papers on this sort of thing now. She worked with Ian Joughin originally with SAR data, and she's continuing the same kind of work. Velocity mappings that we do. So these different signatures tell you things primarily about things like how the subglacial water system evolves over the course of the season, and whether or not there's a lot of bedrock control, whether or not there's a lot of control by the ice front of the glacier calving away at some point in the spring. As I pointed out, we do global coverage of glacier velocity. Here's a map that Mark Vonstock's responsible for of southeastern Alaska flow. We have a time series of this, and we can see that several of these glaciers over the course of the Landsat 8 period have surged. And we get a nice detailed temporal mapping of how the surge begins and then spreads up and down the glacier. It's really a rich data set, and it's available. And again, just to hammer home the global sense, we're looking at Svalbard here, some of the islands in the Franz Josef Archipelago, Novaya Zemlya, where they don't let you do ground field work because there's too much crazy stuff the Russians have dumped there. And so everything has to be done by satellite, but we get good imagery of all of these remote ice caps. And that's it. If you have any questions, let me know. I'm going to risk putting the video back. Well, maybe you can put the video back on. And I will stop the share so we can ask Ian as well as me.
Okay, fantastic. Well, thank you very much, both Ted and Ian, for those presentations. I learned quite a bit about NISAR and Landsat 8 and 9. Ted, I was hoping, can you describe a little more about how Landsat 9 will distinguish itself from Landsat 8 and its predecessors briefly? You said the sensors being built right now will have even more radiometric resolution?
No, the sensor that's being built right now for Landsat 9 is identical to Landsat 8. It'll just be in an orbit that shifts by half a cycle. So we'll have essentially same path and row repeat, but on an 8-day cycle instead of a 16-day cycle. The way Landsat 9 will distinguish itself is that it hopefully will have a better thermal sensor, which is a completely different trail of products and ideas, applications. Landsat 8's thermal sensor, it has 2 channels, but only one of them is clean enough to use. That means no split window and some other things. It's quite useful the way it is, but you kind of need to join it with, say, MODIS thermal data in order to really understand what's going on in a quantitative sense.
Okay, so maybe the theme for ice flow studies for Landsat 9 is if it ain't broke, don't fix it.
It's a wonderful sensor. In fact, rarely, in my experience, has there ever been a sensor that was so overbuilt in terms of capability as the OLI sensor. It actually internally has 14-bit resolution. And there's a little discussion about trying to send down the 14-bit resolved images, but that's a huge increase in the data rate. And so I think so far people have said 12 bits fine, we're still exploring what we can do with that. But the sensor actually has 14-bit radiometry internally. And the geolocation is excellent. So we're able to do this velocity mapping fairly easily because images out of the box are almost perfectly geolocated. We get a long way with just that, and then we do some later adjustments when we stack up images in the mosaic to take out the remaining. It's usually between 3 and 6 meters shift between one image to the next. It's really gone very well. Landsat 8 has had very few problems except for the thermal sensor. Hopefully Landsat 9 will have the same luck. And from what I've seen, Sentinel-2A and B also have, it's generally good news about how well their sensors are working.
Okay, great. Thank you. I happily open it up to questions from the rest of the audience. Have at it. I know there's I learned last time through Tim Bartholomew that there was some sort of hand-raising option, but I'm not seeing that right now. Sarah, do you want to explain that a little bit?
So there is a hand-raising option, but I think the best thing to do is just unmute yourself and ask your question. If for some reason you're having trouble unmuting, just send a note in the chat box, and you can get to the chat at the bottom.
Okay, great. Anyone?
Wow, we just nailed every question.
Well,
not really. Can you hear me or not?
Yes, we can.
I'm Igor from Dark Green Screen. Igor Appel. The title of your presentation included snow. And do you have a team working with seasonal snow? Not glaciers, but seasonal snow. And what is a good information, the way to get the information?
Yeah, I think once we've integrated Sentinel-2 data, and maybe wait for Landsat 9, but I think Sentinel-2 will be the big change. We have in our funded plan the goal of looking at seasonal snow cover using VIS-IR data sets. That's a big task. A lot of people have worked very hard on handling fractional snow cover within a pixel. I'm not anticipating that we would attempt to repeat their work. Let's see, how do I put this? We'll either collaborate with the team, and one of them is right there at NSIDC that's working on that sort of thing, or we'll do a simpler approach. But basically, you need lots of imagery. And because the snow cover in the Northern Hemisphere extends to much lower latitude, you need the wider swath of Sentinel-2 to get reasonable frequent coverage. So yes, I probably should have taken that out of the title as we approached giving the talk, because because I didn't have time to show the graphics that we put into the proposal, which say we're planning to do the snow cover mapping in this and that fashion. We don't have any snow cover results yet.
But is it possible to get from you personally that information about plans? Not now, but send it to your mail.
Yes, I can do that.
Thank you.
Igor, can you send me your email? Maybe you see my email already, but I'm teds@nsidc.org.
Okay, I'll do it.
Okay, great. Thank you.
And by the way, I'm interested in fractional snow cover. The most difficult issue to explain.
Yes, very difficult.
Okay, but it is my preference to get
fractional snow cover.
Okay, thank you. I'll send you my email request.
Great, thanks, Igor. I see Nick Holshoe had a question for Ian.
And David Sheen also.
Yeah, and David Sheen as well. Yeah.
Yeah, so Nick's asking about the pink area in the Antarctic map over Queen Maud Land. That is the a box around the Indian station there, where they would also collect S-band data as well as L-band data.
And there was also a pink box in, I think it was Svalbard.
Yeah, they had interest in acquiring S-band data there too. I think they have a research station there.
And the S-band, can you remind us what wavelength that would be, and whether or not that, I'm guessing expected to have broader value across the entire ice sheet compared to the L-band?
It would what? Sorry, broader?
With the S-band, we wouldn't be using, NISAR for ice flow mapping wouldn't generally use the S-band, would it?
It would generally use the L-band.
L-band, yeah.
L-band, S-band might be useful. There may be some low SNR dark areas that it would be better to have some S-band data. But primarily, we're planning on using the L-band data. Because NASA's providing the L-band instrument and India's providing the S-band instrument, all of our requirements have to be met with the L-band instrument only, just so NASA can sort of sign off on meeting requirements with not relying on the Indian instrument. That said, we will probably end up using more of it than we've planned to use. There are some limitations on it's much more thermally constrained than on how much data it can collect per orbit with S-band relative to L-band. So there will be a couple, at least a few complete imagings of Antarctica with S-band, but more to get the imagery rather than interferometry.
Okay. So
is thermally constrained? How did you mean? What do you mean thermally constrained? Do you mean it's
the
more?
Radar heats up too much if it's on too long.
Ah, okay.
So Chris Larson just completed Icebridge, Alaska, and sent around a report, and that includes some photos of some remarkably dirty Alaskan glaciers. I wonder if S-band might be of value there.
It could be. We'll certainly have plenty of S-band coverage of the Indian glaciers or Himalayan glaciers.
Those are pretty debris covered too. Yeah.
S-band is longer wavelength than L-band, isn't that correct?
No, it's about half. It's between C and L.
Okay.
I think the British did that to confuse people in World War II.
It worked. Great. Any other questions from the audience? You can raise your hand if you click on the participant list, and then I'll see you.
I see a question from David Sheen. Around the coastline, that's the sea ice mode, which is a low bandwidth mode because there's an awful lot of sea ice in the world, or for now there is anyway.
Yeah. Great. Okay, so thanks. So we're just about out of time. I'd like